স্যার আপনি থাকবেন না?
আমি থাকবো।
হ্যাঁ রেডি স্যার আপনারা একটু ওকে রেডি করতেছি স্যার। সবাই একটু থামস আপ করো। ওকে কমপ্লিট।
ঠিক আছে ভাই,
না না বাইরে দিলাম
मरम के नहीं गिरते हैं।
Of the current, because in current, the tip and the boron nitride monolayer, which is dope, it can move up and down because we're keeping the current constant. You can see here height, the blue is nearer and red is further away. So for silicon boron nitride, silicon nitride at nitrogen side and silicon at boron side. So what it helps Dr. Thomas or any experimental colleague is you take the sort of STM picture. Now he has some simulation picture, and depending on his sort of measured observed picture or diagram, he can say, aha, silicon is the next topic about the phosphorine. And what we see here is in bulk. It exists in sort of three forms. We have the white phosphorus, and again, as you know, it's dangerous. Melting point is 44 degrees. Then we have a red phosphorus. It's pretty high melting point. But we also have a black phosphorus. And it's simply exfoliate. Like a graphene, a graphite, we do graphene. One can sort of make a monolayer of phosphorine from black phosphorus crystal. So here is the tri-layer, three layers of this phosphorine material, and what you can see here is not like an in-plane configuration. Phosphorus has a 5 electrons, and depending on the bond between phosphorus and phosphorus, it forms. The exfoliation energy is again reasonable. The calculated value is about 100 milli-electron volts per atom. And then what we find is one of the density function theory, sort of one of the modeling elements is you have to have van der Waals-like interaction term, which we found it is very important for this case, like in graphene. So this is the monolayer, and the advantage you can see is it has this is the valence band, this is the conduction band, and this is the lead gap. And interestingly, if you look at the calculate the band structure, if you go number of layers from 1 to bulk, it's sort of like convergence. So monolayer has about 1.4, 1.5 electron volts. For the bulk, if you come down, it's about 0.3, 0.48. So the tunability comes in, depends on the layer thickness of the material. It has a very high hole mobility, which is again important. The direct band gap, but again it's a 1.5 electron volt. If I go to any device physicist, he said, I have a material which has a gap of 1.5 electron volt, is it a good material? He said no. It has to be around 0.2, 0.3, 0.4 electron volt to make a good field effective transistor devices, the FETs. So idea is can we modify the gap without changing the mobility? Mobility is definitely required for these FET devices. So look at the periodic table state. And what you find here is a direct band gap, and which is a finite. So oxygen forming a bond with phosphorus, again gives a finite band. And if you look at the electron density of bands, this is the maximum valence band, minimum of conduction band, and you have a hybrid sort of orbitals coming in, crystal orbitals, forming these valence and conduction bands. So this is a fully sort of functionalized, a fully oxidized monolayer of phosphorine. Let's see what happens when we vary the functionality. What about the partial functionalization? So we picked up again 3 cases. So we have a half functionalized, we have a quarter, and we have 1/8. So what we find here is, after doing all these calculations, equivalent configuration, and so on, is the nature of the band gap changes as you move from pristine phosphorine to fully functionalized phosphorine oxide. And here's the case. If I look at the bare or the pristine case, so we have, this is the direct band gap, and red is indirect band gap. So phosphorine bare and fully functionalized, the direct band gap is sort of minimum related to indirect band gap, which is good for optoelectronic applications. But the partial functionalization, what you see, the indirect gap is lower than the direct gap. This is again the STM curve. We can see here is IV characteristics depending on functionalization, current changing. And this is a pristine phosphorine, the calculated STM figure, and this is a fully oxidized phosphorine oxide for the case. So what we found is here is phosphorine in oxygen is robust. It forms a very stable finite band gap material, phosphorine oxide. That's just coming out as a prediction. So what we look into it, that literature, and we notice is that experiments have shown that the aging effect in phosphorine-based electronic devices. Its phosphorine is unstable in air. So here is the experimental work. This is an as fabricated phosphorine. This is about 30 minutes, 1 hour, and this is 24 hours. And if you look at the Raman peaks here, you can see here this is the as fabricated, but within 24 hours these peaks are gone. So in a sense, phosphorine is sort of fragmented in air. So the question comes is, if you think about air, sort of oxygen and water, but what we found is oxygen it doesn't do anything. So let's look at the water. How does it interact with the phosphorine monolayer? Again, similar calculation. You have water molecules at the surface coming in and sort of going up and down. And what you find is nothing happens. The phosphorine does not interact with water molecules. So the question comes in, how can we explain the instability of phosphorine in air? So what we propose that phosphorine first interacts with oxygen.
Checking for brittleness.
Yeah, see, antimony as you see, mono is conducting as carbon-carbon bond.
Yeah.
So we have done a lot of calculations, but I have not shown that result.
Okay.
But it's not going to be mechanically strong as graphene.
Yeah, that one.
Because the bond.
Yeah. Okay, I will talk to you later then. Things, these are the minimum things we have checked so that we can compare with the experimental.
Look at the bulk, like
Yes.
composites, aluminum oxide, Al2O3, Dr. Thomas has done it, is well properties, electron properties, and see how good they are in comparison to the experiment. So once you have this thing, then you have confidence about the model of aluminum and oxygen. Similarly, you can do for carbon, you can pick up the graphite, a diamond.
So this is this is the other way. Like we just carry out the experimental first and then see what are the things that we can from. But the other way, just like we predict something, just like you said. So what are the checks? That means
This check is 20 years of experience. Because I know my model elements, I know everything we have done phosphorine group 5 elements. So if the model elements work with phosphorine, expectation is going to work for anyone. And see, always remember, prediction is going to be qualitative. I'm not claiming it's going to be the band gap or the thing. Simply saying it's going to be stable with a finite band gap. That's it.
Yeah, then like we see the formation energy or
ICMS2020, there is a token gift to all these keynote speaker and invited speakers. Sir, please. So Professor Sabutamash is being given this gift, token gift by the chair of this technical session. Okay, sir, please stay on the dais. So Professor Pande is being given the gift. So thank you, sir. Thank you, Professor Pande, for chairing this session. Thank you all. So here is an announcement. This is the time for lunch. Little time will be there, and after the lunch there will be a poster session. Actually, you know this, in ICMS2020 posters are coded in different codes, and here are the codes for having the posters: NMNC, AM, OEMS, SEMD. So these codes during 2:10 to 3:40 p.m. and that is just after lunch break. So after completion of this poster session, there will be the
Maybe I'll wait for 10 15 minutes. So let them the final one.